In this video, I'm going to talk about the use of the energy bucket model and problems that involve Newton's universal law of gravitation, where objects are very, very far from the Earth, and we use a different model for force and energy. So here's a planet here. I'm going to take a look at a planet and object that's in an elliptical orbit around it. So I'm going to say there's an object here like a satellite or a moon, and it's going to orbit, and it's going to go in an elliptical orbit, so a little further over here and come back a little closer on this side. I'll call this point A on here and point B on the other side. This planet has a mass, I'll call it capital M, and this satellite or planet is, I'll call that little m. Okay, so this object's going to have a velocity here, call it VA on one side and VB on this side. Now I'm doing these 2 points, but any 2 points in the orbit you can analyze. You can analyze any 2 points. And then just to be clear here, this is the distance from the center of the planet here to point A is RA right there, and the distance from the center of the planet to B is RB. So it's a B right there, RB. So whenever we measure these distances, again, always measure from the center of the planet. So if you're given an altitude, you have to make sure to include the radius. Okay. So what our goal is here is to find the velocity at point B, find VB. Okay, and I'm going to walk through all the steps of the energy model, which is basically the same. The only real difference in this is, well, kinetic energy is the same. It's still 1/2 mv squared. But potential energy due to gravity is, we use a different model. It's minus G, Newton's universal gravitational constant, the mass of the planet, the mass of the satellite, divided by R. And these are the 2 R's that we have here. So basically I'm just going to substitute this equation in. Instead of mgh or mgy, I'm going to use this one instead. And also note that when you use this equation, normally the ground level is the reference line, because that's where potential energy is 0. If you put a baseball on the ground, that's 0 energy. Here you can see that this becomes 0 when R goes to infinity. Basically, way out here, way out in a deep space at infinity, when R equals infinity, that's when the potential energy becomes 0. So this is really our new reference line, way out in infinity. Really won't come into play in this problem, but you'll see how it comes into play in later problems. But we just draw it there for consistency. So step 1, draw a reference line. Out at infinity is my reference line. Step 2 is statement of conservation of energy. So I'm going to say energy at point A is equal to the energy at point B. And so here's my point A and point B. Alright, so they're clearly denoted there. Again, you could have analyzed point C or D or E or F. We'd have to make sure we know the distances. Now I'm going to draw my energy bucket. So I have my kinetic energy bucket right here. And because potential energy due to gravity is negative, I'm going to draw an upside down bucket for that. And on the other side, another kinetic energy bucket here. And another gravitational potential energy bucket here. Okay, and what I did, if you notice, I make sure I draw the baseline here. So definitely draw the potential energy due to gravity lower or upside down from this baseline, just so you see a visual of positive and negative. Kinetic at A, potential due to gravity at A, kinetic at B, and gravitational at B. Okay, so let's see, it is moving. Okay, it does have gravitational at point A, although negative. It's a negative quantity there. It does have kinetic at B. We're going to try to find that out, what the velocity is, and there's gravitational at B. Right? So we fill in all the buckets here. And again, same thing. I'm going to just write a 1-for-1 correspondence for the equations. 1/2 mva squared minus gm over ra. Make sure our distances are right here. Equals 1/2 mvb squared minus g capital M lowercase m over rb, distance to b. All right, and then so we'll solve here for velocity b. But you can also, before we do that, you can see that the little m's actually cancel. So the mass of that orbiting satellite actually does not matter, which in conservation of energy problems usually is the case. So the mass doesn't matter. which is consistent with Newton's law of gravitation. When you have two different mass objects, they fall at the same rate. So that seems to work out. I see a 1/2 here, so I'm going to multiply both sides by 2 to kind of get that out of there. So this just to simplify the math here a little bit, I'll put a multiply both sides by 2. Okay, so the solve part is VA squared minus 2, there's that 2 I just multiplied, GM over RA equals VB squared, because I multiplied by the 2, minus G capital M over RB. Okay, so really with this equation, given any information, and if we can solve for anything, I could give you velocities and radii, and you could solve for the mass of a planet. That's actually how one way they can do it. They with astronomical observations, look at velocities and radii of different things and solve for the mass of a planet. Here we'll solve for the velocity b. So VB is equal to, let's see, VA squared. So this is minus 2 GM M over RA, and then this goes to the other side, so that becomes plus 2 GM over RB, and I square root that, and that should give me velocity of B. And then I'll box my answer. So if you look at the big picture here, what I did is I used the exact same energy bucket model. The only thing I really changed is the potential energy buckets. Instead of using our typical MGH or MGY, we use our new model. Okay, reference Einstein's at infinity. I know my buckets, write my equation term per term, and then solve. So that's how you can apply the energy bucket model to problems involving our new model for gravitational potential energy because of Newton's law of gravitation.